2.5 million light-years away, something is looking back. The Andromeda Galaxy stretches its spiral arms around nearly 1 trillion stars, and at its center lurks a black hole 140 million times the mass of our Sun. Recently, the James Webb Space Telescope pierced its core with infrared vision, and what it revealed has forced scientists to rethink everything we believed about our nearest galactic neighbor, a long, quiet giant showing signs of awakening, the ancient scars of galaxies it once consumed, and unmistakable evidence that our encounter with this cosmic colossus has already begun. If you enjoy what comes next, remember to like and subscribe. Let's begin. On a clear autumn night, you can see it with the naked eye, a faint, misty glow near the constellation Cassiopeia. Most people pass without a second glance, unaware they are staring at a galaxy of nearly 1 trillion suns, compressed into a spinning disk more than 220 light-years wide. This is Andromeda, the closest large galaxy to our own, and it is moving directly toward us. For more than a century, astronomers have studied this vast island of stars. They traced its spiral arms, catalogued its clusters, and measured its distance at roughly 2.5 million light-years from Earth. The number sounds unimaginable, yet on the scale of the universe, Andromeda is practically next door and closing in. The Milky Way and Andromeda are the two largest galaxies in what scientists call the local grouper collection of more than 50 galaxies bound together by gravity. But here is what makes your spine tingle. Andromeda is not standing still. Every second it races toward us at roughly 70 miles per second. That is over 250 mph. At that speed, you could circle Earth 10 times in 60 minutes. The galaxy has been on this collision course for billions of years, and nothing in the universe can stop what comes next. The James Webb Space Telescope changed everything when it turned its golden mirrors toward Andromeda. Unlike Hubble, which sees visible light the way human eyes do, Webb sees in infrared heat signatures, hidden structures, things that have been invisible to every telescope that came before. When Webb focused on Andromeda's core, scientists expected to see a sleeping, quiet galactic center minding its own business across the void. They were wrong. What Webb revealed sent shock waves through the astronomical community. The images showed something stirring at the heart of Andromeda. Unusual bursts of radiation, distorted clouds of gas, structures that should not exist according to standard models. One researcher described the data as deeply unsettling. Another called it the most significant discovery about Andromeda in decades. The telescope captured details no human instrument had ever seen before. Filaments of superheated material spiraling inward, dust rings glowing with infrared light, star clusters behaving in ways that defied explanation. And at the very center, wrapped in layers of gas and ancient stars, sat the monster itself, supermassive black hole, one that might be waking up. The implications are staggering. If this black hole is increasing its activity, it could reshape the entire galaxy before our two cosmic islands ever collide. But the truly terrifying part, what Webb discovered, suggests the collision between Andromeda and the Milky Way might be more violent, more chaotic, and closer than anyone predicted. Your eyes are liars. They show you less than 1% of what actually exists. The visible spectrum, the rainbow of colors you see every day, represents just a thin slice of electromagnetic radiation. Beyond violet lies ultraviolet, X-rays, and gamma rays. Beyond red lies infrared, microwaves, and radio waves. Most of the universe operates in frequencies you will never see. That is where the James Webb Space Telescope enters the story. Launched in December 2021, Webb does not see the universe the way you do. Its instruments are tuned to infrared wavelengths, the heat signature of the cosmos. This gives Webb a superpower that Hubble never possessed. It can peer through cosmic dust that blocks visible light completely. Think of it like this. Imagine trying to see through a thick fog with your eyes impossible. Now imagine having thermal vision that detects heat instead. Suddenly, the fog becomes transparent. That is exactly what Webb does when it looks at galaxies like Andromeda. When Webb pointed its 6.5-meter mirror at Andromeda, it saw structures that had been hidden for billions of years. Dust lanes that appeared dark and empty in visible light suddenly blazed with infrared energy. These lanes are not empty at all. They are packed with cool stars, molecular clouds, and organic compounds, the kind of material that builds new solar systems. The telescope uses two main instruments to dissect galaxies. The near-infrared camera, NIRCam, captures sharp images of stellar populations, and the mid-infrared instrument, MIRI, detects cooler objects like dust grains and aging stars. Together, these tools create a complete portrait of a galaxy's hidden anatomy. But here is where it gets strange. When scientists examined Webb's infrared data from Andromeda's core, they noticed something peculiar: temperature variations that made no sense. Regions that should be cooling down were instead heating up. Gas clouds showed unusual motion patterns, spiraling inward faster than gravitational models predicted. Confirmed observations revealed dust rings surrounding the galactic center glowing brightly in mid-infrared wavelengths. These rings are not uniform. They have gaps, distortions, and clumps that suggest recent disturbances. Something has been stirring up material in Andromeda's core within the last few million years. In cosmic time, that is yesterday, Webb also detected specific chemical signatures that previous telescopes missed entirely. Complex carbon molecules, organic compounds, elements forged in the hearts of dying stars and scattered across the galaxy. The infrared spectrum acts like a barcode, telling scientists exactly what elements exist and in what quantities. The detail is breathtaking. Webb can resolve individual star clusters in Andromeda that Hubble could barely distinguish as blurry dots. It can measure the temperature of gas clouds down to fractions of a degree. It can trace the spiral arms deeper into the galaxy than ever before. Yet, with each new layer of detail comes new questions. The more clearly we see Andromeda, the less we seem to understand about what is happening at its core. And that invisible monster lurking in the center Webb just gave us our first real look at what it is doing. What scientists found there defies everything they thought they knew about dormant black holes. Numbers lose meaning at galactic scales. Your brain cannot truly comprehend what 1 trillion means. If you counted one star per second without sleeping or stopping, it would take you 31,700 years to count them all. That is how many stars burn inside Andromeda right now. Each one is a nuclear furnace. Most are smaller and cooler than our star. Some are massive blue giants that will explode within a few million years. Others are ancient red dwarfs that will burn for trillions of years into the future. All of them orbit a common center of gravity, held together by the invisible hand of dark matter that outweighs the stars themselves by 6 to 1. The James Webb Telescope can resolve individual stars in Andromeda's outer regions, not all of them, of course, that would be impossible. But Webb can pick out the brightest giants, the massive stars that shine with the power of 10, 0, or even 100, 0 times the luminosity of our star. These stellar beacons serve as markers, allowing scientists to map the galaxy's structure in unprecedented detail. Hubble photographed over 200 million stars in Andromeda during a survey that took over a decade. Those images created the most detailed mosaic of another galaxy ever assembled. But Hubble operates primarily in visible light. It saw the bright young stars and missed countless others hidden by dust. Webb is now filling in the gaps, revealing the cool red giants and the dusty stellar nurseries where new stars are forming. Star formation in Andromeda happens differently than in the Milky Way. Our galaxy produces roughly 7 new stars per year. Andromeda creates fewer, perhaps 2 or 3. Scientists theorize this difference comes from Andromeda's violent history. The galaxy appears to have undergone a major collision several billion years ago, an event that used up much of its available gas. With less raw material, fewer stars can form. But Webb discovered something unexpected. Certain regions of Andromeda are creating stars at surprisingly high rates, far exceeding what models predicted. These stellar nurseries hide in the spiral arms, wrapped in thick cocoons of dust that visible light telescopes cannot penetrate. Webb sees right through them. The temperature readings are particularly revealing. Newborn stars are hot, blasting their surroundings with ultraviolet radiation. This heats up nearby dust, causing it to glow in infrared wavelengths. Webb can measure this glow and calculate how many young stars must be present. The numbers are higher than expected in several key regions. Why would certain parts of Andromeda suddenly become more active? One theory points to gravitational interactions with satellite galaxies. When a small galaxy passes close to Andromeda, its gravity compresses gas clouds, triggering bursts of star formation. Another theory suggests that Andromeda's own spiral arms create compression waves that periodically squeeze gas into dense clumps. The sheer mass of all these stars is staggering. Andromeda contains roughly 1.5 trillion times the mass of our Sun, counting both the stars themselves and the dark matter halos surrounding them. The Milky Way, by comparison, holds only about 800 billion solar masses. Andromeda is nearly twice as massive as our home galaxy. This size difference matters greatly. When two galaxies collide, the larger one usually dominates. And in 4 billion years, when these two cosmic titans finally meet, Andromeda will be the bigger predator. But there is something else lurking at the center of all those stars, something that makes the trillion burning spheres look tiny by comparison. At the exact center of Andromeda, in a region smaller than our solar system, sits an object that weighs more than 100 million stars combined. It is invisible, it emits no light. It is a supermassive black hole, and for most of human history, it has been asleep. Black holes do not actually sleep, of course, but they can be quiet or loud depending on how much material they are consuming. When a black hole actively feeds on gas and stars, it becomes one of the brightest objects in the universe. The infalling matter heats to millions of degrees, creating a blazing accretion disk that screams across every wavelength from radio waves to gamma rays. Astronomers call these active galactic nuclei, and they can outshine their entire host galaxy. Andromeda's black hole is not like that. For millions of years, it has been classified as dormant. It sits there, warping space-time into an inescapable pit, occasionally snacking on a stray gas cloud or unlucky star. The radiation it produces is faint, barely detectable even with powerful X-ray telescopes. Scientists compare it to Sagittarius A, the supermassive black hole at the center of the Milky Way, which is also remarkably quiet. Then came the X-ray observations that changed everything. The Chandra X-ray Observatory has been watching Andromeda's core since the year 2000. For over 15 years, it recorded a steady but dim X-ray signal from the central black hole. Occasionally, the signal would spike a brief flare lasting hours or days, then back to baseline. These flares happened every few years and seemed random. In 2006, Chandra detected an unusually strong flare. The X-ray brightness jumped by a factor of 100, flooding the central region with high-energy radiation. Then it faded again. Scientists filed it away as interesting but not alarming. Black holes burp sometimes. Maybe a small gas cloud fell in, maybe a star wandered too close. But in 2013, it happened again, another powerful flare. And this time, something strange accompanied it. The Ice Cube Neutrino Observatory in Antarctica detected a burst of neutrinos coming from the direction of Andromeda. Neutrinos are ghost particles that barely interact with matter. They are produced in extreme environments, places where matter is being torn apart under unimaginable forces. The correlation was unsettling. 2 X-ray flares, 2 neutrino bursts, both coming from the same source, both suggesting that something violent was happening at Andromeda's core. Recent analysis, published in 2025, confirmed that the black hole has remained in an elevated state of activity since 2006. The baseline X-ray emission is higher than it was before. The flares are more frequent. This is confirmed data. The black hole is behaving differently than it did 20 years ago. The question is why. One theory suggests that Andromeda recently captured a dense gas cloud or possibly a small galaxy remnant. As this material spirals toward the black hole, it would produce exactly the kind of elevated activity scientists are seeing. Another theory is more disturbing. Perhaps the black hole is naturally cycling into an active phase. Perhaps what we consider dormant is just the calm before the storm. If the black hole is truly waking up, the consequences would ripple across the entire galaxy. Jets of radiation could blast through Andromeda's core. Star formation could be suppressed or triggered depending on the intensity. And when the Milky Way finally collides with Andromeda billions of years from now, we might be facing not one but two active supermassive black holes. The James Webb Telescope added another piece to this puzzle. Its infrared observations revealed something Chandra could not see. Gas clouds near the black hole are moving faster than they should. Something is accelerating them. And the most terrifying question of all remains unanswered. If this black hole is waking up now, what will it look like when it reaches full activity? Mass warps reality. When you pack enough matter into a small enough space, you rip a hole in the fabric of space-time itself. That is what sits at the center of Andromeda supermassive black hole, with a mass estimated at 140 million times that of our Sun. To understand how monstrous this is, consider the black hole at the center of our own galaxy. Sagittarius A weighs roughly 4 million solar masses, already an incomprehensible object, already powerful enough to fling stars around at thousands of miles per second. Andromeda's black hole is 35 times more massive. The event horizon, the point of no return around a black hole, expands with mass. For Sagittarius A, the event horizon has a radius of about 12 million miles. You could fit 17 suns side by side across that distance. Andromeda's black hole has an event horizon roughly 35 times larger. The sphere of doom surrounding it stretches over 400 million miles across. That is wider than the orbit of Mars. Anything crossing that boundary is gone, forever, not destroyed instantly as science fiction sometimes suggests, but stretched and shredded by tidal forces as it spirals inward. Physicists call this spaghettification. A human falling toward the black hole would be pulled apart, their feet experiencing far stronger gravity than their head, until they were torn into a stream of atoms. But nothing is falling in right now. The space around Andromeda's black hole is remarkably empty. This is why it stays so quiet. A black hole without fuel is just a gravitational well sitting in the dark. Scientists measured the mass of this monster by watching how stars near the galactic center move. These stars orbit at incredible speeds, thousands of miles per second, whipping around the central point in elliptical paths. By tracking their motion over years, astronomers can calculate exactly how much mass must exist at the center to produce those orbits. The answer came back at 140 million solar masses, give or take 20 million. The uncertainty exists because measuring distances and velocities across 2.5 million light-years is phenomenally difficult. The discovery of this black hole happened in 1991 using the Hubble Space Telescope. Hubble's sharp vision could resolve the very center of Andromeda and detected something strange. The nucleus appeared doublet-woe, bright concentrations of stars separated by just 5 light-years. For years, astronomers debated what this meant. Was Andromeda digesting a smaller galaxy? Did it have 2 black holes? Further observations solved the mystery. The galaxy has only one central black hole. The double appearance comes from an eccentric ring of stars orbiting it. These stars do not travel in circles. They move in elongated ellipses, causing them to bunch up at certain points in their orbit. This creates the illusion of 2 bright cores when viewed from Earth. Why would stars orbit in such strange patterns? The leading theory is that Andromeda's black hole merged with another black hole in the past. When 2 supermassive black holes spiral together and finally collide, they release gravitational waves powerful enough to kick the surrounding stars into chaotic orbits. The evidence suggests this merger happened perhaps a few 100 million years ago, though. This remains a theory, not confirmed fact. What is confirmed is the mass. What is confirmed is the hunger. And what scientists are now discovering, thanks to Webb, is that new material is starting to feed this sleeping titan. Thin streams of gas are falling toward the center, not enough to wake the black hole completely, but enough to keep it simmering at a higher level than before. The question everyone is asking is simple: how much longer until it fully wakes up? Black holes do not swallow everything nearby like cosmic vacuum cleaners. They are surprisingly picky eaters. Material needs to lose angular momentum to fall in, which means gas and dust must shed their orbital energy somehow. This happens through friction, magnetic fields, and gravitational interactions. The result is a slow, spiraling descent toward oblivion. The James Webb Telescope revealed exactly how Andromeda's black hole feeds. Long filaments of gas and dust stretch from the outer regions of the galactic center, winding inward in elegant, deadly spirals. These structures were always there, but previous telescopes lacked the resolution and infrared sensitivity to see them clearly. Webb changed that. The filaments glow in infrared light because they are warm. As gas falls toward the black hole, friction heats it up. The material rubs against itself, generating temperatures of thousands of degrees. This is still relatively cool compared to the millions of degrees reached closer to the event horizon, but hot enough to emit strongly in the infrared wavelengths Webb detects. Scientists using combined data from Hubble and the Spitzer Space Telescope had previously glimpsed hints of these structures, but Webb's images are the clearest view yet. The filaments look like cosmic waterfalls, streams of matter pouring toward the center from multiple directions. Some originate from dense molecular clouds in the galactic disk. Others come from disrupted star clusters that wandered too close. The feeding process is not continuous. It happens in bursts. A large clump of gas falls in over the course of weeks or months, causing a spike in radiation. Then the black hole goes quiet again as it waits for the next meal. This is confirmed by the X-ray observations showing sporadic flares every few years. What makes the current situation unusual is the increased frequency of these feeding events. Over the past 2 decades, the black hole seems to be snacking more often. This suggests something has changed in the central region. Perhaps gravitational interactions from Andromeda's satellite galaxies are funneling more gas toward the core. Perhaps the galaxy's spiral arms are compressing material and sending it inward. Webb's infrared data showed another disturbing detail. Some of the filaments are moving faster than expected. The gas is accelerating as it approaches the black hole, which is normal, but the speeds measured are higher than gravity alone should produce. This hints at additional forces at play. Magnetic fields perhaps channeling the gas along specific paths, or jets of material being blown out from the black hole's poles, creating pressure that pushes nearby gas around. Near the very center, within a few light years of the black hole, the filaments become chaotic. The orderly spiral breaks down into turbulent eddies and swirls. This is the accretion zone, where material is moving at significant fractions of light speed, heated to extreme temperatures and torn apart by tidal forces. Even Webb cannot resolve details this close to the event horizon. The region is too small and too bright, but the outer filaments tell the story clearly. The black hole is being fed slowly for a trickle rather than a flood. Yet the feeding rate is increasing. More gas is finding its way to the center than was arriving 100 years ago. If this trend continues, Andromeda's black hole could transition from dormant to moderately active within the next few million years. In cosmic time, that is imminent. For humanity, it is so far in the future that our species may not exist to witness it. Unless, of course, the feeding accelerates faster than predicted. Unless something catastrophic happens to dump a massive amount of material into the core all at once. And when the Milky Way collides with Andromeda in a few billion years, that is exactly what will happen. When Hubble first photographed the center of Andromeda in 1991, astronomers could not believe what they saw. Instead of one bright nucleus, there were two distinct concentrations of light separated by roughly 5 light-years. The brighter one, labeled Pone, sits slightly off-center. The dimmer one, called P2, occupies the true center of the galaxy. For years, this double nucleus sparked heated debate. The most popular theory suggested Andromeda had recently cannibalized a smaller galaxy, and Pone was the remnant core of that victim-captured nucleus orbiting the true center before eventually being torn apart and absorbed. It was a dramatic explanation that fit with the evidence that large galaxies grow by eating smaller ones. But this theory had problems. If Pone was a captured galaxy core, it should not be stable. The tidal forces from Andromeda's main black hole would rip it apart in just a few million years. Yet Pone appeared intact and organized. The timeline did not work. Further observations with improved instruments revealed the truth. 2. The dimmer concentration is where the supermassive black hole actually resides. It is surrounded by a compact disk of hot blue stars. These stars are spectral class, are young and massive, and they emit strongly in ultraviolet light. In blue and ultraviolet images, P2 appears brighter than Pone. In red and infrared images, Pone dominates. So, what is Pone? The answer turned out to be more interesting than a captured galaxy. Pone is part of an eccentric stellar disk that orbits the black hole. The stars in this disk do not travel in neat circles. Their orbits are stretched into long ellipses. As they move around the black hole, they bunch up at the opposite to the point farthest from the center. This creates a concentration of stars that appears as a separate bright region. Think of it like cars on a racetrack with a sharp curve. The cars slow down as they enter the curve and bunch together. From above, you would see a concentration of vehicles at that spot. The same thing happens with stars in eccentric orbits around Andromeda's black hole. But why would stars orbit in such bizarre patterns? The leading explanation is gravitational recoil from a black hole merger. When two supermassive black holes spiral together and collide, they release gravitational waves. These waves carry momentum, and if the two black holes have different spins or masses, the merged black hole can be kicked in one direction. This kick disturbs the orbits of nearby stars, flinging them into eccentric paths. Computer simulations support this idea. When astronomers model a black hole merger at the center of a galaxy, the resulting stellar distribution looks remarkably similar to what we see in Andromeda's core. The merger would have happened several 100 million years ago, long enough for the system to partially settle, but not long enough for the eccentric orbits to decay into circles. This means Andromeda's central black hole is itself a product of collision. It likely formed when two smaller black holes, each weighing tens of millions of solar masses, merged into the current monster. And if Andromeda's black hole has already undergone one merger, it will certainly undergo another in 4 billion years. When the Milky Way and Andromeda collide, their central black holes will eventually spiral together. The 4 million solar mass black hole from our galaxy will meet the 140 million solar mass giant from Andromeda. The collision will release gravitational waves so powerful they will ripple across the universe. But we are getting ahead of the story. First, you need to understand how Andromeda became the monster it is today, and that means looking at the scars it carries from its violent past. Galaxies are not peaceful places. They are battlefields where gravity reigns supreme. The strong consume the weak, the large devour the small. Andromeda is no exception. It is a cannibal that has been feeding on its neighbors for billions of years. The evidence is written in the stars themselves. Astronomers studying Andromeda's stellar populations discovered something remarkable. The galaxy's outer halothy diffuse cloud of old stars surrounding the main disk contains distinct streams of stars moving in organized patterns. These streams are not random. They are the shredded remains of smaller galaxies that Andromeda captured and tore apart. When a dwarf galaxy falls into the gravitational well of a giant like Andromeda, tidal forces stretch it into a long ribbon. The galaxy's stars are stripped away over millions of years, spread out along its orbital path. Eventually, the dwarf galaxy disappears completely, its stars absorbed into the halo of the larger galaxy. But the stream they create can persist for billions of years, a ghostly marker of what once existed. Scientists using the Hubble Space Telescope map dozens of these stellar streams in Andromeda's halo. By analyzing the ages and chemical compositions of the stars in each stream, they reconstructed the galaxy's merger history. What they found was shocking. Andromeda has consumed at least 100 to 200 smaller galaxies over the past 12 billion years. Some were tiny dwarf galaxies containing only a few million stars. Others were substantial spiral galaxies with billions of stars. The most significant merger happened relatively recently in cosmic terms, just a few billion years ago. This collision brought a massive influx of stars and gas into Andromeda, triggering bursts of star formation and completely reshaping the galaxy's structure. Evidence for this event shows up in the ages of stars. Many of Andromeda's stars are between 2 and 4 billion years old, suggesting a major episode of star formation during that period. But there was another merger, much older, that happened roughly 10 billion years ago. This ancient collision involved a galaxy perhaps one-fifth the mass of the Milky Way's substantial meal. The stars from this merger now form part of Andromeda's inner halo, a spherical cloud of old metal-poor stars surrounding the galactic center. The chemical signatures tell the story clearly. Stars born in small dwarf galaxies have different element ratios than stars born in large galaxies. Small galaxies form stars slowly, so their stars are enriched primarily by long-lived, low-mass supernovae. Large galaxies form stars rapidly, so their stars contain elements from massive, short-lived supernovae as well. By measuring these ratios in Andromeda's halo stars, astronomers can identify which galaxy each star originally came from. This is confirmed data. The stellar streams exist. The chemical evidence is unambiguous. Andromeda has been violently assembling itself for over 10 billion years, and the process is still ongoing. Right now, several dwarf galaxies orbit Andromeda. They are doomed. Over the next few billion years, they will spiral inward, stretched and torn apart by tidal forces, until nothing remains except new streams in the halo. Andromeda will continue growing, feeding, preparing for its ultimate collision. The Milky Way is not innocent either. Our galaxy has its own history of cannibalism. We are currently in the process of consuming the Sagittarius dwarf elliptical galaxy, a small system that has already made multiple passes through the Milky Way's disk. We will finish eating it within the next few 100 million years. But when Andromeda and the Milky Way finally meet, it will not be a small galaxy being devoured by a large one. It will be two titans locked in mutual destruction. Both galaxies will be forever transformed, and the scars they leave on each other will persist for billions of years. The ghosts of dead galaxies are watching. They know what comes next. Imagine tearing apart a city brick by brick and scattering the debris across 1,000 miles. Years later, a detective could still reconstruct what happened by analyzing the patterns in the rubble. That is what astronomers do when they study galactic halos. The halo of Andromeda extends far beyond the bright spiral disk visible in photographs. It stretches outward for hundreds of thousands of light-years, a vast, nearly invisible sphere of old stars and dark matter. This halo contains the memories of every galaxy Andromeda has ever consumed. Using deep imaging from the Hubble Space Telescope, a team of astronomers catalogued the globular clusters in Andromeda's halo. Globular clusters are dense balls of ancient stars, typically containing hundreds of thousands of members packed into a sphere just a few dozen light-years across. They orbit galaxies like satellites, immune to the chaos of the galactic disk below. Andromeda has over 400 of these clusters, far more than the Milky Way's roughly 150. Each cluster tells a story. By measuring how fast it moves and in what direction, astronomers can trace its orbit backward in time. Clusters that orbit in similar planes and at similar speeds likely came from the same original dwarf galaxy. The halos of consumed galaxies do not disappear immediately. When Andromeda tears apart a dwarf galaxy, the victim's dark matter halo, its globular clusters, and its stars all get redistributed. But they maintain some coherence for billions of years. They move as a group, orbiting Andromeda in patterns that betray their origin. In 2019, astronomers published a groundbreaking study revealing that Andromeda's globular clusters separate into two distinct populations. One group orbits in a relatively flat plane, moving in the same direction as the main galaxy's rotation. These are likely native clusters, born when Andromeda itself formed over 12 billion years ago. The other group moves on wildly inclined orbits, some even going in the opposite direction. These are the Invaders clusters captured from smaller galaxies. But it gets more specific. The captured clusters themselves split into two subgroups based on their orbits and ages. One subgroup appears to be the remnants of a merger that happened roughly 2 billion years ago. The other subgroup is much older, dating back to a merger around 10 billion years ago. Two distinct cannibalistic events, each leaving a unique signature in the halo. This is galactic archaeology. By studying the present-day distribution of stars and clusters, scientists reconstruct the violent history that created the galaxy we see today. It is like excavating ancient ruins to understand a civilization that disappeared millennia ago. The stars in these ghost halos are metal-poor, meaning they contain fewer heavy elements than stars born recently. This makes sense. Small dwarf galaxies form stars slowly, so they do not produce as many heavy elements through supernovae. When Andromeda absorbed these galaxies, it inherited their metal-poor stars, which now populate the outer halo. Webb's infrared observations added new details to this story. By measuring the temperatures and compositions of individual red giant stars in the halo, astronomers can determine their ages more precisely. Some stars are over 12 billion years old, nearly as ancient as the universe itself. Others are just a few billion years old, born during relatively recent mergers. The spatial distribution matters too. Stars from the most recent merger are concentrated in specific regions of the halo. Stars from the ancient merger are spread more evenly, having had billions of years to disperse. All of this paints a clear picture. Andromeda is a serial killer of galaxies. It has been hunting and consuming neighbors for its entire existence, and it shows no signs of stopping. Right now, multiple dwarf galaxies orbit within its gravitational reach, spiraling slowly inward to their doom. The Milky Way is heading straight into the jaws of this predator, but unlike the dwarf galaxies Andromeda has consumed before, our galaxy has the mass to fight back. What happens when two equal predators meet? Over 400 globular clusters orbit Andromeda like a swarm of ancient bees. Each cluster is a city of stars, hundreds of thousands of them, bound together by gravity in a sphere that could fit inside the distance from our Sun to its nearest neighbor. These clusters are relics from the early universe, formed over 12 billion years ago when the first galaxies were assembling. Globular clusters are among the oldest objects in the cosmos. The stars within them are metal-poor, born before the universe had been enriched with heavy elements from multiple generations of supernovae. They shine with a dim reddish light, the color of aging giants that have burned through most of their hydrogen fuel. Andromeda has far more globular clusters than the Milky Way. Our galaxy hosts roughly 150 confirmed clusters. Andromeda has over 400, possibly closer to 500 when you count the faintest ones. This difference is significant. The number of globular clusters a galaxy possesses correlates with its merger history. More mergers mean more clusters. Each time Andromeda consumed a dwarf galaxy, it inherited that galaxy's globular clusters. Small dwarf galaxies might contribute just a few clusters. Larger galaxies could bring dozens. Over billions of years, Andromeda accumulated a vast population from its cannibalistic conquests. The most massive globular cluster in Andromeda is designated B23G78. It contains several million stars and likely harbors an intermediate mass black hole at its core, weighing close to 100 solar masses. This cluster is so dense and massive that it might actually be the stripped core of a small galaxy that Andromeda devoured long ago. When a dwarf galaxy is torn apart, sometimes its central nucleus survives as a dense stellar remnant. Webb's observations are helping scientists study these clusters in new ways. Infrared imaging can penetrate the dense cores of globular clusters and resolve individual red giant stars. By measuring the brightness and color of these giants, astronomers determine the cluster's age and chemical composition with unprecedented precision. The orbital motions of these clusters reveal Andromeda's dark matter distribution. Dark matter is invisible, but it exerts gravitational pull on everything around it. By tracking how globular clusters move over years and decades, scientists map the invisible dark matter halo that dominates Andromeda's mass. This halo extends far beyond the visible galaxy, stretching perhaps 1 million light-years into space. But here is where things get unsettling. Some of Andromeda's globular clusters are moving faster than they should. Their velocities suggest they are being influenced by gravitational perturbations from something we cannot see. The most likely explanation is ongoing interactions with infalling dwarf galaxies. As a dwarf galaxy spirals into Andromeda, its gravity tugs on nearby globular clusters, accelerating them into unusual orbits. This means the merger process is active right now. Andromeda is currently in the act of consuming at least one, possibly several, small galaxies. These victims are in various stages of destruction. Some are mostly intact, still recognizable as distinct objects. Others have been stretched into long streams, their stars spread across hundreds of thousands of light-years. Eventually, they will all disappear into Andromeda's halo. The clusters themselves will survive. Globular clusters are incredibly resilient. Their stars are packed so tightly that the cluster holds together even when subjected to strong tidal forces. They can pass directly through the disk of a galaxy and emerge on the other side intact. When Andromeda and the Milky Way eventually collide, the globular clusters from both galaxies will intermix, creating a new population numbering over 500. For now, these ancient clusters orbit Andromeda in silent testimony to the galaxy's violent history. They are the gravestones of dead civilizations, markers of galaxies that no longer exist, and they are a preview of what awaits the Milky Way. When our galaxy falls into Andromeda's gravity well, our globular clusters will join theirs, swirling together in the merged halo of a new cosmic monster. The collision has not started yet, or has it? Andromeda does not hunt alone. It travels through space accompanied by an entourage of at least 14 confirmed satellite galaxies, with possibly more waiting to be discovered. These small galaxies orbit the giant, trapped in its gravitational field, slowly spiraling inward toward their doom. The largest and most famous of these satellites is Messier 32, a compact elliptical galaxy that orbits Andromeda at a distance of about 24 light-years from its center. Messier 32 is unusual. It looks like the stripped core of a much larger galaxy. Its outer regions appear to have been torn away, leaving only the dense central bulge. Scientists theorize that Messier 32 was once a substantial spiral galaxy, but repeated close passes through Andromeda's disk have shredded its outer stars and gas. Another prominent satellite is Messier 110, a dwarf elliptical galaxy with a smoother, more intact structure. It orbits further out than Messier 32 at roughly 190 light-years from Andromeda's center. Messier 110 still contains some young stars, evidence of recent star formation which is unusual for an elliptical galaxy. The gravitational interaction with Andromeda may have compressed gas clouds in Messier 110, triggering bursts of new stars. Then there are the ultra-faint dwarf galaxies. These tiny systems contain only a few thousand stars and are almost impossible to detect. They are dominated by dark matter, with dark matter outweighing visible stars by ratios of 100:1 or even higher. Astronomers discovered many of these dwarfs only in the past 2 decades using deep surveys with advanced telescopes. The satellite galaxies do not orbit randomly. Several of them move in a coherent planar thin disk of galaxies, all orbiting in roughly the same direction. This structure, called the Great Plain of Andromeda, has puzzled astronomers for years. Why would satellite galaxies arrange themselves in such an organized pattern? One theory suggests they are the remnants of a larger structure that Andromeda disrupted. Perhaps a stream of galaxies fell into Andromeda's gravity well along a specific trajectory, creating the planar distribution we see today. Another theory invokes the tidal forces from the Milky Way, which could be pulling Andromeda's satellites into alignment. But regardless of how they got there, their fate is sealed. Gravitational interactions will cause these satellites to lose orbital energy over time. They will spiral inward, passing closer and closer to Andromeda's core with each orbit. Eventually, tidal forces will tear them apart, spreading their stars across Andromeda's halo. This process is already underway for several of the satellites. Stellar streams extending from them have been detected, evidence that they are being actively shredded. The James Webb Telescope can observe individual stars in some of these satellite galaxies. By studying their ages and chemical compositions, scientists learn about the environment in which they formed. Dwarf galaxies are fossil relics from the early universe. They formed quickly and then mostly stopped making stars. Their stellar populations are old and metal-poor, providing a window into what conditions were like over 12 billion years ago. Interestingly, some of Andromeda's satellites appear to have been affected by reionization, a cosmic event that happened roughly 13 billion years ago when the first stars and galaxies flooded the universe with ultraviolet light. This radiation ionized neutral hydrogen throughout space, making it harder for small galaxies to hold onto their gas. Many dwarf galaxies stopped forming stars during this period, frozen in time as relics of the early universe. The gravitational dance between Andromeda and its satellites has been ongoing for billions of years. Some satellites have already been consumed, others are in the final stages of disruption. A few might survive for another billion years before succumbing. And the Milky Way? We have our own collection of satellite galaxies, including the large and small Magellanic Clouds. When Andromeda and the Milky Way collide, their satellite systems will merge too. The survivors will orbit the new combined galaxy, assuming they are not flung into intergalactic space by the violence of the collision. But something even more unsettling has been discovered. The collision between the Milky Way and Andromeda is not a future event. In a very real sense, it has already begun. For decades, astronomers described the Andromeda collision as a distant future event, something that will happen in 4 billion years. A cosmic catastrophe so far away that humans need not worry about it. That description is no longer accurate. In 2020, scientists working on Project Omega made a startling discovery. Omega stands for Absorption Map of Ionized Gas in Andromeda, a program that uses the Hubble Space Telescope to study the galaxy's halo. They were mapping the vast cloud of gas surrounding Andromeda when they found something unexpected. The halo is far larger than anyone realized. Andromeda's halo of hot, ionized gas extends roughly 1 million light-years from the galaxy's center in all directions. That is an enormous envelope of thin plasma heated to temperatures of hundreds of thousands of degrees. This gas is invisible to normal telescopes, detectable only through its absorption of background ultraviolet light. The Milky Way has a similar halo, a vast cloud of hot gas and dark matter that extends far beyond the visible galaxy. Recent measurements suggest our halo also reaches out to roughly 1 million light-years. Here is the problem. Andromeda is only 2.5 million light-years away. If both galaxies have halos extending 1 million light-years in all directions, then the halos are already touching. In fact, they have likely been in contact for over 1 billion years. This is confirmed observational data. The collision between the Milky Way and Andromeda has already started. We are currently passing through the outer reaches of Andromeda's halo, and Andromeda is passing through ours. The interaction is so subtle that we do not notice it. The gas in the halos is incredibly thin, barely a few atoms per cubic meter. It exerts no drag on the galaxies themselves, but the implications are profound. These two cosmic islands are not separate entities moving through empty space. They are gravitationally bound to each other, locked in an inexorable dance that will end in merger. The halos are the first parts to interact. Over the next few billion years, the interaction will intensify. The halos will compress and heat up where they overlap. Eventually, the visible disks of the galaxies will begin to deform under each other's gravity. Computer simulations show what comes next. In roughly 2 billion years, Andromeda will appear larger in Earth's night sky, assuming Earth still exists and still has a breathable atmosphere. The galaxy will stretch across tens of degrees, a spectacular sight dominating the heavens. But it will not be a peaceful view. By that point, tidal forces from Andromeda will be distorting the Milky Way's spiral arms. In roughly 3.7 billion years, the first close approach happens. The two galaxies will swing past each other, their disks beginning to interpenetrate. This will trigger massive bursts of star formation as gas clouds collide and compress. The night sky will blaze with millions of newborn stars, blue and brilliant, lighting up emission nebulae across vast regions of space. After the first pass, the galaxies will swing apart again, pulled by their mutual gravity into elliptical orbits around each other. But they will not escape. In another billion years, they will collide again, more violently this time. The spiral structures will be completely disrupted. Stars will be flung in all directions. Some solar systems will be ejected into intergalactic space, orphaned from any galaxy. By roughly 7 billion years from now, the merger will be complete. The two galaxies will have combined into a single elliptical galaxy, a massive blob of stars with no discernible structure. Astronomers have already given this future galaxy a name, Milkomeda, or alternatively, Milkdromeda. But recent research has added uncertainty to this timeline. A 2025 study using data from the Gaia spacecraft and Hubble telescope found that when you account for the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy, the probability of a collision drops to roughly 50%. There is a real chance the two galaxies will swing past each other and never fully merge within the next 10 billion years. This is the current state of scientific understanding. The collision is no longer certain. The timeline is uncertain. What is certain is that the Milky Way and Andromeda are gravitationally bound. Their halos are already interacting. And we are living through the early stages of one of the most significant cosmic events in the local group's history. Whether the collision happens in 4 billion years or 10 billion years or not at all, one thing remains true. Andromeda is heading toward us, and we are heading toward it. And what happens when they finally meet? The timeline seems impossibly distant, 4 billion years. To put that in perspective, 4 billion years ago, Earth was a barren rock. No plants, no animals, not even single-celled life as we know it today. The first bacteria were just beginning to appear in the primordial oceans. Everything that has happened since then, all of evolution, all of human history, spans a period shorter than the time remaining until the collision. 4 billion years from now, Earth will be unrecognizable if it even still exists. The biggest threat to our planet is not the galactic collision, it is our own star. Over the next several billion years, our sun will gradually increase in brightness. This is a natural consequence of aging. As hydrogen fuses into helium in the core, the helium ash accumulates, increasing the core's density and temperature. This makes the fusion reactions run faster, releasing more energy. In roughly 1 billion years, our sun will be about 10% brighter than it is today. That may not sound like much, but it will be enough to trigger a runaway greenhouse effect on Earth. The oceans will begin to evaporate. Water vapor is a powerful greenhouse gas, trapping more heat, which evaporates more water, creating a feedback loop. Within a few 100 million years, Earth will resemble Venusa's scorched, lifeless world with surface temperatures hot enough to melt lead. By the time Andromeda and the Milky Way actually collide, our sun will be roughly 35 to 40% brighter than today. Earth will be long dead. The habitable zone, the region around a star where liquid water can exist, will have moved outward. Perhaps Mars or the moons of Jupiter will be habitable by then, or perhaps life will have migrated to a different star system entirely. Assuming humanity or its descendants still exist, they will have a front-row seat to the most spectacular cosmic event imaginable. The night sky will be transformed. Andromeda will stretch from horizon to horizon, a swirling mass of billions of stars. The two galaxies will interpenetrate, their disks passing through each other like ghosts. Individual stars will not collide. Space is too empty for that. The average distance between stars is several light years. A galaxy is mostly empty space with occasional dots of light scattered throughout, but the gas will collide. When massive clouds of hydrogen and helium slam into each other at speeds of hundreds of miles per second, they compress and heat up. This triggers intense bursts of star formation. Simulations predict that millions of new stars will be born during the collision, lighting up the merged galaxy with a blue glow. Stellar nurseries will appear everywhere. Giant molecular cloudsomes stretching hundreds of light-years across will collapse into clusters of hot young stars. These stars will be short-lived. The most massive ones will explode as supernovae within just a few million years, enriching the surrounding gas with heavy elements and triggering new waves of star formation. Our own sun will likely survive the collision unscathed. The probability of a direct stellar collision is vanishingly small. However, our star's orbit around the galactic center will change dramatically. Currently, our Sun sits about 26.0 light-years from the Milky Way's core, orbiting at a sedate speed of roughly 140 miles per second. After the merger, simulations suggest we will be flung much farther out, perhaps 50.0 light-years from the new galactic center. There is also a small chance, roughly 12%, that our solar system will be completely ejected from the merged galaxy. Gravitational interactions during the collision could give our star enough velocity to escape entirely. We would become an intergalactic wanderer, drifting through the void between galaxies with no galactic disk to call home. But the most dramatic event will happen at the very center of the merged galaxy. The two supermassive black holes, one from each galaxy, will spiral toward each other over millions of years. When they finally collide, they will release a burst of gravitational waves powerful enough to be detected by civilizations thousands of galaxies away. That collision is still billions of years in the future. Or maybe it is not. Recent data has introduced doubt. What if the galaxies miss each other entirely? When two supermassive black holes collide, reality itself shivers. The fabric of space-time ripples outward in waves of gravitational energy, traveling at the speed of light across the universe. This is not science fiction. This is confirmed physics, predicted by Einstein over a century ago and directly observed by the LIGO and Virgo detectors in 2015. The Milky Way's central black hole weighs roughly 4 million times the mass of our Sun. Andromeda's weighs 140 million solar masses. When these two monsters finally spiral together, the merger will release more energy than all the stars in the observable universe combined, at least for the brief moment of collision. But getting to that point takes time. Black holes do not simply crash together. They orbit each other, slowly spiraling inward as they radiate gravitational waves. This process can take hundreds of millions of years, depending on the initial separation and orbital velocities. When the two galaxies first collide, the black holes will be separated by tens of thousands of light years. They will begin a long, slow dance toward the center of the merged galaxy. Dynamical friction, the gravitational drag caused by passing stars and gas cloud swill, gradually rob them of orbital energy. With each pass, they move closer together. Eventually, when the separation drops to a few light years, gravitational wave emission becomes the dominant force. The black holes radiate energy as gravitational waves, causing their orbit to decay rapidly. They spiral faster and faster, whipping around each other at significant fractions of light speed. In the final seconds before merger, the two black holes will be orbiting each other hundreds of times per second. The gravitational waves they produce will have frequencies in the range detectable by space-based observatories. If humanity still exists and still builds telescopes, this will be the astronomical event of the millennium. The collision itself lasts only a fraction of a second. The two event horizons touch and merge, creating a single larger black hole. But the merger is not clean. The combined black hole will be violently spinning and highly distorted. It will ring like a bell, oscillating as it settles into a stable configuration. This ring-down phase emits a final burst of gravitational waves before the black hole becomes quiet again. The final mass will be roughly 144 million solar masses, the sum of the two original black holes. However, a small amount of mass, perhaps 1 to 5%, will be converted directly into gravitational wave energy during the merger. This energy radiates outward at light speed, carrying with it information about the masses, spins, and orbital parameters of the black holes. If the two black holes have different spins, the merger can produce a recoil kick. The merged black hole can be ejected from the galaxy center at speeds of hundreds or even thousands of miles per second. This is a real phenomenon predicted by simulations and possibly observed in a few galaxies. If it happens during the Milky Way and Andromeda merger, the resulting galaxy would have no central black hole for millions of years, until the kicked black hole eventually falls back to the center. The stars near the black holes will be profoundly affected as the black holes spiral together. They gravitationally scatter nearby stars, flinging them in random directions. Some stars will be accelerated to escape velocity and shot out of the galaxy. Others will be captured into tight orbits around the merged black hole, doomed to eventual tidal disruption. The surrounding gas will be disrupted as well. Any gas that was orbiting one of the original black holes will be stirred up by the merger. This could trigger a burst of accretion onto the newly formed black hole, lighting it up as an active galactic nucleus. For a few million years, the center of Andromeda might shine as brightly as a quasar, outshining the combined light of all its stars. This is the fate awaiting the cores of the Milky Way and Andromeda. Two black holes, born from the deaths of countless stars, will merge into a single cosmic monster at the heart of a new galaxy. But before that can happen, something even more chaotic must occur. The galaxies themselves must collide. The name sounds whimsical. Milkomeda, a portmanteau of Milky Way and Andromeda, coined by astronomers to describe the galaxy that will be born from their collision. But there is nothing whimsical about the process that will create it. When two spiral galaxies merge, the outcome depends on several factors: the mass ratio between the two galaxies, the amount of gas remaining in their disks, the angle and speed of the collision. For the Milky Way and Andromeda, simulations predict the result will be a giant elliptical galaxy. Elliptical galaxies look nothing like spirals. They have no disk, no spiral arms, no organized rotation. They are bloated, football-shaped clouds of stars with random orbits. Most of the stars in an elliptical galaxy move on chaotic paths that cross through the galactic center repeatedly. The overall structure is smooth and featureless, lacking the intricate beauty of a spiral. Why do mergers produce ellipticals? The collision destroys the organized rotation of the two spirals. Stars are flung in all directions by gravitational interactions. The orderly orbits that created the spiral arms become scrambled. By the time the merger completes, the stars are moving on random trajectories, creating the spherical or ellipsoidal shape characteristic of ellipticals. Milkomeda will be massive. The combined mass of the Milky Way and Andromeda will approach 2 trillion solar masses when you include dark matter. In visible stars alone, Milkomeda will contain roughly 1.3 trillion stars, making it one of the largest galaxies in the local group. The central bulge will be enormous. Both the Milky Way and Andromeda have substantial bulges-dense concentrations of old stars at their centers. When the galaxies merge, these bulges will combine, creating a superbulge that dominates the inner region of Milkomeda. Star formation will spike during the merger, then rapidly decline. When gas clouds collide during the galactic encounter, they compress and fragment, triggering bursts of new star formation. Simulations suggest millions of massive stars will be born over a few 100 million years. These stars will be hot and blue, giving Milkomeda a temporary bluish tint. But the star formation cannot last. Mergers are efficient at using up available gas. The collision will funnel gas into the galactic center, where some will form stars and some will be consumed by the central black hole. Whatever gas remains will be heated to temperatures too high to collapse and form new stars. Within 1 billion years after the merger completes, Milkomeda will have exhausted most of its star-forming gas. This means Milkomeda will age quickly. Without new stars being born, the galaxy will gradually redden as its massive blue stars die and only the long-lived red stars remain. In 10 billion years, Milkomeda will be a red and dead elliptical galaxy composed almost entirely of old, low-mass stars, slowly fading over trillions of years. The size of Milkomeda is harder to predict. Elliptical galaxies are puffier than spirals. When you scramble the orbits of stars, they spread out, creating a larger overall structure. Milkomeda might span over 200 light-years in diameter, larger than either of its parent galaxies. But Milkomeda will not be alone. The Triangulum galaxy, the third largest member of the local group, will likely join the merger. Triangulum is a small spiral galaxy about 60 light-years across. It currently orbits Andromeda at a distance, but gravitational interactions during the Milky Way and Andromeda collision could pull Triangulum into the fray. If that happens, Milkomeda will absorb Triangulum as well, growing even more massive. Over the next 150 billion years, all the remaining galaxies in the local group will fall into Milkomeda. Dozens of dwarf galaxies, leftover satellites, everything gravitationally bound to the local group, will eventually merge into a single giant elliptical galaxy. This is the future of our cosmic neighborhood, not stars scattered across multiple galaxies, but one massive island of light surrounded by the expanding void of intergalactic space. And somewhere in that galaxy, orbiting far from the core, might be a yellow star that was once called home. If it survives the collision, not every star will make it into Milkomeda. When galaxies collide, the gravitational chaos flings some stars completely out of the system. They become hypervelocity stars, orphans traveling through the intergalactic void with no galaxy to call home. Hypervelocity stars are real. Astronomers have discovered dozens of them in the Milky Way stars moving at speeds exceeding 370 miles per second. That is fast enough to escape the galaxy's gravity entirely. Most of these stars were likely ejected by gravitational interactions with the supermassive black hole at the galactic center. A binary star system wandered too close. One star was captured, the other was flung outward at incredible speed. During the merger of the Milky Way and Andromeda, this process will happen on a massive scale. Simulations predict that roughly 10 to 20% of the stars in both galaxies could be ejected into intergalactic space. That is hundreds of billions of stars cast into the void. Imagine living on a planet orbiting one of these ejected stars. You would grow up in a galaxy with a bright disk of stars overhead, a spiral of light stretching across the night sky. Then, over the course of a few million years, that disk would begin to recede. The galaxy would shrink, becoming smaller and dimmer as your star accelerated away. Within 10 million years, the galaxy would be just a bright smudge in the distance. Within 100 million years, it would be a faint patch of light, indistinguishable from the other galaxies scattered across the sky. Your star would be alone, drifting through the darkness between galaxies, with no neighbors closer than millions of light years. The night sky from such a planet would be nearly black, no Milky Way arcing overhead, no bright galactic core, just a scattering of distant galaxies, each a faint, fuzzy blob, and perhaps a few hundred stars from your own ejected cluster, if you were lucky enough to be part of a group. This fate is not guaranteed for every star. Most stars will remain bound to Milkomeda, but the ones near the edges of the galaxies during the collision are at risk. Gravitational slingshots will accelerate them beyond escape velocity, condemning them to eternal isolation. Some of these hypervelocity stars will be traveling so fast they escape the local group entirely. They will cross the tens of millions of light years, separating the local group from neighboring galaxy clusters. In a few billion years, they might find themselves falling into the Virgo cluster, captured by the gravity of a completely different group of galaxies. Others will remain bound to the local group, but outside Milkomeda. They will orbit the merged galaxy at enormous distances, forming an extended halo of isolated stars. Over trillions of years, some might fall back into Milkomeda. Others will remain in the outer darkness forever. The ejection process is not random. Stars in the outer regions of each galaxy are more likely to be flung away. Stars in the dense central bulges are more likely to remain bound. This means elliptical galaxies like Milkomeda tend to have lower mass halos than their parent spirals. The collision strips away the outer stars, leaving only the tightly bound core. Our solar system sits in the outer disk of the Milky Way. We are not in the safest location. Simulations give us roughly a 12% chance of being ejected entirely. That is not a high probability, but it is not negligible either. There is a real chance that when the collision occurs, our star will be flung into intergalactic space. If that happens, future inhabitants of Earth, assuming any exist, will witness the galaxy receding into the distance over millions of years. They will become true cosmic nomads, wandering the void between the galaxies. But there is another possibility, one that is far more likely. Our star might remain bound to Milkomeda, but its orbit will change dramatically. Where will we end up? Right now, our Sun orbits the Milky Way at a distance of roughly 26 light-years from the galactic center. We complete one orbit every 230 million years. Dinosaurs walked the Earth the last time we were on the opposite side of the galaxy. This orbit is stable, predictable, and has been essentially unchanged for billions of years. That stability is about to end. When the Milky Way collides with Andromeda, every star in both galaxies will have its orbit violently disrupted. Gravitational interactions will fling stars in random directions, scrambling the orderly rotation of the spiral disks. Our star will not be exempt. Simulations show the most likely outcome. Our star will be kicked outward, pushed to a distance of roughly 50 light-years from the center of Milkomeda. That is almost twice our current distance from the Milky Way's core. We will become outer halo stars, orbiting far from the bright central bulge where most of Milkomeda's stars will concentrate. The view from Earth, if Earth still exists, will be dramatically different. Currently, the Milky Way's disk stretches across our night sky as a bright band of light. From our new location in Milkomeda's outer halo, the galactic disk will no longer surround us. Instead, we will see the entire galaxy as a distant glowing sphere. The central bulge will be the brightest feature concentrated ball of old red stars dominating the sky. The night sky will be darker overall. Fewer stars will be visible to the naked eye because we will be farther from the densest stellar regions. The galaxy will look less like the Milky Way we know, and more like a distant elliptical galaxy, except much brighter because we will still be part of it. Our orbital speed will change as well. Stars in the outer halos of elliptical galaxies move on highly eccentric orbits. Instead of a nice circular path, our star might follow an elongated ellipse that carries us close to the galactic center before swinging back out to the halo. These plunging orbits can take hundreds of millions of years to complete. There is also the 12% chance of complete ejection. As mentioned earlier, if that happens, we become an intergalactic wanderer. Our star will leave Milkomeda entirely, drifting through the void with no galaxy to orbit. The night sky will be almost completely dark except for scattered distant galaxies. But here is the critical point. None of this affects Earth's habitability. The collision between galaxies happens on scales of thousands of light-years. Our star's immediate neighborhood, the region within a few light-years, will be completely undisturbed. The planets will continue orbiting exactly as they do now. The asteroid belt will remain stable. The Oort cloud will stay bound to the outer solar system. Individual stars will not collide. The distances between stars are too vast. Even in the densest regions of the galactic core, stars are separated by light-years. The chance of a direct stellar collision during the merger is less than 1 in a trillion. However, there is a small risk of a near pass. If another star swings within a few light-years of our solar system, its gravity could disturb the Oort cloud, sending comets raining into the inner solar system. This could trigger a bombardment similar to the late heavy bombardment that Earth experienced 4 billion years ago. Such an event would be catastrophic for any life on Earth. The probability of this happening is low, probably less than 1%. Most likely, our star will simply be relocated to a new orbit in Milkomeda without any close encounters. Our planetary system will remain intact. The only thing that changes is our position in the galaxy and the view of the night sky. Of course, all of this assumes Earth is still habitable when the collision occurs. As mentioned earlier, our Sun's increasing luminosity will likely make Earth uninhabitable within 1 billion years, long before the galaxies fully merge. Any life that witnesses the collision will either be living on a different world or will have migrated to another star system entirely. Our star's fate is uncertain in detail, but certain in broad strokes. We will survive the collision, we will be relocated to a new orbit, and we will spend the rest of our existence as citizens of Milkomeda, the giant elliptical galaxy born from the merger of our two cosmic homes. But what is happening right now at Andromeda's core suggests the collision might be more violent than anyone expected. The Chandra X-ray Observatory has been watching Andromeda's core for over 2 decades. X-rays reveal the most violent processes in the universe: superheated gas, matter spiraling into black holes, neutron stars colliding, Chandra sees what visible light telescopes cannot, the high-energy chaos hidden at galactic centers. For years, Andromeda's central black hole produced a faint, steady X-ray signal. The baseline emission came from hot gas in the immediate vicinity, material heated to millions of degrees by friction and magnetic fields. This was expected. Even quiet black holes emit some X-rays from their accretion zones. Then the flares began. In 2006, the X-ray brightness suddenly spiked. The emission jumped by a factor of 100 within hours. The black hole was screaming in X-rays, blasting its surroundings with high-energy radiation. The flare lasted several days before fading back to baseline. Astronomers noted it as interesting but not alarming. Black holes occasionally have indigestion when they swallow large clumps of gas. 7 years later, it happened again. Another massive X-ray flare erupted from the core. This one was even more powerful than the first. The timing seemed random. No obvious trigger, no visible disturbance in the surrounding gas. The black hole simply erupted without warning. Since then, the baseline X-ray emission has remained elevated. The black hole never returned to its previous quiet state. It continues producing X-rays at a higher rate than before 2006. The flares also continue smaller outbursts happening every few years. Recent analysis published in 2025 examined 15 years of Chandra data. The study confirmed what many astronomers suspected. The black hole is in a new phase of activity. Something changed around 2006. The exact cause remains unknown, but the pattern is clear. X-ray flares of this magnitude suggest violent accretion events. Material falling into the black hole does not descend smoothly. It spirals inward, heating up as it goes. When a particularly dense clump of gas reaches the inner accretion disk, it can trigger a sudden release of energy. The gas compresses, heats to extreme temperatures, and emits a burst of X-rays before disappearing past the event horizon. But there is another possibility. The flares might be related to magnetic field reconnection. Magnetic fields can become twisted and tangled in the chaotic environment near a black hole. When these field lines snap and reconnect, they release enormous amounts of energy in seconds. This process is similar to solar flares on our sun, but billions of times more powerful. The hardness of the X-rays provides clues. Hard X-rays have higher energies than soft X-rays. By measuring the ratio of hard to soft X-rays, astronomers can determine the temperature and density of the emitting gas. Andromeda's flares produce relatively soft X-rays compared to the Milky Way's black hole when it flares. This suggests different physical conditions in the two accretion zones. The connection between X-ray flares and the black hole's overall activity level is significant. If the feeding rate is increasing, we would expect more frequent and more powerful flares. That is exactly what the data shows. The black hole is eating more than it was 20 years ago. This has profound implications. If Andromeda's black hole is transitioning from dormant to active, the galaxy's core will transform over the next few million years. Active black holes produce jets-powerful beams of particles and radiation that blast out from the poles at near light speed. These jets can extend for hundreds of thousands of light years, far beyond the galaxy itself. No jets have been detected yet from Andromeda's core, but if the accretion rate continues increasing, jets might form. And when the Milky Way and Andromeda eventually collide, an active black hole will make the merger far more violent than simulations currently predict. The X-rays are a warning. The black hole is waking up, and what it does next could reshape the entire galaxy. But X-rays are not the only strange signals coming from Andromeda's core. 14 confirmed satellite galaxies orbit Andromeda. Probably more lurk undiscovered in the depths of space. But what disturbs astronomers is how these satellites are arranged. They do not orbit randomly. They move in a coherent structure, a thin, rotating plane that astronomers call the Great Plane of Andromeda. This should not exist. When small galaxies fall into a large galaxy's gravity well, they should arrive from random directions. Over billions of years, they should scatter into a spherical cloud around the host galaxy. That is what standard cosmological models predict. That is what dark matter simulations show. Andromeda's satellites defy these predictions. At least half of them orbit in a plane just 13, 0 light-years thick but stretching hundreds of thousands of light-years across. The plane itself rotates, with satellites moving in the same general direction like planets around a star. This degree of organization is statistically improbable. The discovery was made by carefully measuring the velocities of satellite galaxies using ground-based telescopes. When astronomers plotted the three-dimensional positions and motions of these satellites, the planar structure became obvious. It cannot be a coincidence. Something created this arrangement. Several theories attempt to explain it. One suggests the satellites are remnants of a larger structure that fell into Andromeda as a group, perhaps a filament of galaxies, a cosmic highway of matter connecting larger galaxy clusters passed near Andromeda billions of years ago. As the filament encountered Andromeda's gravity, it was shredded, leaving behind a stream of smaller galaxies all moving in the same direction. Another theory points to tidal forces from the Milky Way. The gravitational pull from our galaxy might be stretching Andromeda's satellite system, causing the satellites to preferentially occupy certain orbits. Computer simulations show this could create a planar structure over billions of years. But these theories have problems. The plane is too thin and too stable. Gravitational interactions should have disrupted it by now. The satellites should have scattered into more random orbits. Yet, the plane persists. A more disturbing possibility exists. What if our understanding of dark matter is incomplete? Dark matter is invisible, detectable only through its gravitational effects. We know it exists because galaxies rotate too fast to be held together by visible matter alone. We know it outweighs normal matter by roughly 6 to 1, but we do not know what it actually is. If dark matter has properties we have not discovered yet, it could create structures that standard models do not predict. Perhaps dark matter can form disks or planes under certain conditions. Perhaps Andromeda's dark matter halo is not spherical but flattened. This could channel satellite galaxies into preferred orbits. This is speculative, not confirmed science. But the great plane of Andromeda is real. It is confirmed observational fact. Something created this structure, and current models struggle to explain it. The James Webb Telescope is helping to refine our understanding by studying individual stars in some of these satellite galaxies. By measuring their ages and chemical compositions, astronomers can determine when and where these galaxies formed. If they all formed at the same time from the same material, that would support the filament theory. If they have diverse histories, the mystery deepens. Some satellites in the plane are being actively torn apart. Stellar streams extend from theme vidants of tidal disruption. These streams are the death throes of small galaxies, the final moments before they are completely absorbed into Andromeda's halo. The satellites outside the plane show different characteristics. They tend to be smaller, older, and more metal-poor. They likely fell into Andromeda's gravity well long ago and have had billions of years to scatter into random orbits. The satellites in the plane are relative newcomers, captured more recently, still maintaining some coherence from their original infall trajectory. Regardless of how it formed, the great plane of Andromeda is doomed. Over the next few billion years, gravitational interactions will scatter the satellites. The plane will thicken and eventually dissolve, and when the Milky Way collides with Andromeda, any remaining satellites will be flung in all directions by the chaos of the merger. For now, the ring of dwarf galaxies orbits in eerie synchronization, a structure that should not exist, surrounding a galaxy that is preparing to devour them all. And beneath that ring, hidden structures are glowing in wavelengths only Webb can see. Dust is the skeleton of a galaxy. It traces the spiral arms, outlines the star-forming regions, and hides the most violent processes occurring in the core. Visible light cannot penetrate thick dust. It scatters and absorbs, rendering entire regions of the galaxy invisible to telescopes like Hubble. But infrared light passes through dust like a ghost through walls. When the James Webb Telescope observed Andromeda in mid-infrared wavelengths, it revealed structures that had been hidden for billions of years. Dust rings surrounding the galactic center, glowing with the heat of embedded stars and warm molecular clouds. These rings are not uniform. They have gaps, clumps, and distortions that tell a story of recent violence. The innermost ring sits roughly 3.0 light-years from the black hole. It is dense, packed with cool stars and organic molecules. The dust grains in this ring are complex, containing carbon, silicon, and iron compounds forged in the atmospheres of dying stars. Webb's spectroscopic instruments can identify these compounds by their unique infrared signatures. Temperature measurements show the ring is warmer than expected. Something is heating it from within. The most likely explanation is recent star formation. When massive stars are born, they blast their surroundings with ultraviolet radiation, heating nearby dust and causing it to glow in infrared light. But there is another heat source, the black hole itself. Although it is not actively feeding at a high rate, the material that does fall in releases energy. This energy heats the surrounding gas and dust, creating a warm zone within the innermost few thousand light-years. Webb can measure this heat gradient, tracking how temperature decreases with distance from the center. The second ring sits farther out, roughly 10.0 light-years from the core. This ring is cooler and more fragmented. It appears to be the remnant of a spiral arm that was disrupted during a past merger. When Andromeda absorbed a smaller galaxy a few billion years ago, the collision sent shock waves through the disk, compressing gas and triggering bursts of star formation. The dust ring is what remains. Webb's observations revealed something unexpected in this outer ring. Polycyclic aromatic hydrocarbons, complex organic molecules containing carbon and hydrogen arranged in hexagonal patterns. These molecules are common in space, found in interstellar clouds throughout the universe. But their abundance in Andromeda's dust ring is unusually high. These molecules form in the atmospheres of carbon-rich stars. When these stars die and shed their outer layers, they release these organic compounds into space. The molecules are tough, surviving the harsh radiation environment of the galaxy for millions of years. They play a crucial role in the chemistry of star-forming regions. The gaps in the dust rings are equally interesting. Something has carved channels through the dust, creating relatively clear zones. One possibility is stellar winds from massive stars. Hot, luminous stars produce powerful stellar winds that blow away nearby gas and dust, creating bubbles and cavities. Over millions of years, these bubbles can grow to hundreds of light-years across. Another possibility is that jets from the central black hole carved these gaps. Even a weakly active black hole can produce narrow jets of high-speed particles. If these jets have been intermittently active over the past few million years, they could have cleared channels through the dust rings. The clumps in the rings suggest ongoing star formation. When a dense clump of gas collapses, it fragments into multiple protostars. These young stellar objects are still embedded in their natal cocoons of dust-invisible light, but bright in infrared. Webb can see them clearly, allowing astronomers to count how many stars are currently forming in Andromeda's core. The data shows star formation is happening, but at a modest rate. Andromeda creates fewer stars per year than the Milky Way, despite being more massive. This confirms the theory that Andromeda used up much of its star-forming gas during past mergers, but the dust rings hold another secret. They are moving, rotating around the galactic center at speeds measured by comparing observations taken years apart. This rotation reveals the mass distribution in Andromeda's core, helping astronomers map the invisible dark matter halo. The dust is not just debris, it is a crucial component of galactic ecology. It absorbs ultraviolet light from young stars and re-emits it as infrared. It provides surfaces where molecules can form. It shields star-forming regions from destructive radiation. Without dust, galaxies would look very different. And what Webb sees in Andromeda's dust rings suggests something is disturbing them. The clumps are asymmetric. The temperature gradients are uneven. Something is stirring up the core. Star formation is accelerating in specific regions. New stars are being born in Andromeda right now, not in vast numbers, but in specific pockets where conditions are just right. Gas clouds compressed beyond a critical threshold, temperatures low enough for hydrogen to clump together, densities high enough for gravity to overcome internal pressure. When all these factors align, stars ignite. The James Webb Telescope mapped these star-forming regions with unprecedented precision. By observing in near-infrared wavelengths, Webb can peer into the dusty cocoons where protostars are gestating. These young stellar objects are still accumulating mass from their surrounding disks, not yet hot enough to ignite full hydrogen fusion, but they are warm, glowing in infrared light that penetrates the dust enshrouding them. Andromeda has several major star-forming complexes. The most active sits in the northern spiral arm, roughly 40 light-years from the galactic center. This region contains massive molecular clouds spanning hundreds of light-years, dense enough to birth thousands of stars over the next few million years. Webb's images reveal the internal structure of these clouds. Filaments of dense gas threading through the cloud, cores where the gas has already collapsed into protostars, outflows where young stars are blasting jets of material into space, clearing their surroundings. The level of detail is extraordinary. Individual forming solar systems can be resolved in the nearest regions, but what surprises astronomers is that star formation is not where they expected it. Standard models predicted the most intense star formation should occur in the densest parts of Andromeda's disk, where gas is most abundant. Instead, Webb found active star formation in regions that appeared relatively quiet in visible light observations. These hidden nurseries exist because they are wrapped in thick dust. Hubble saw them as dark patches, regions where starlight is blocked. Webb sees through the dust and reveals the birth chambers of new stars. The temperature of the dust provides crucial information. Hot dust indicates nearby young stars. Cool dust suggests older, more evolved regions. Chemical analysis through spectroscopy reveals what elements these new stars will contain. Gas clouds in Andromeda are metal-rich compared to the Milky Way, meaning they contain higher abundances of elements heavier than hydrogen and helium. This is because Andromeda has experienced more supernova enrichment over its history. Each generation of massive stars that lived and died added more heavy elements to the galactic gas reservoir. The rate of star formation in Andromeda is roughly 2 to 3 solar masses per year. That means every year, enough gas collapses to create 2 or 3 stars the mass of our own Sun. This is slower than the Milky Way's rate of approximately 7 new stars per year. The difference is telling. Andromeda has less available gas, most of it consumed or expelled during past mergers, but some regions show bursts of elevated star formation. These localized spikes correlate with areas where Andromeda's satellite galaxies have passed through the disk. When a dwarf galaxy plunges through a larger galaxy's gas-rich disk, it compresses the gas, triggering a wave of star formation in its wake. This is confirmed by observations showing young star clusters along the orbital paths of several satellites. Webb also detected pre-stellar core clumps of gas that have not yet collapsed into stars but are on the verge of doing so. These cores are cold, just 10 to 20 degrees above absolute zero. They are fragile, barely held together by gravity. Any disturbance could trigger collapse or disperse them entirely. The most massive protostars will become blue giant stars tens of times the mass of our own Sun. They will live fast and die young, exploding as supernovae within just a few million years. Their deaths will seed the galaxy with heavy elements, preparing the next generation of stars and planets. The smallest protostars will become red dwarf stars that will burn for trillions of years. Long after Andromeda and the Milky Way have merged into Milkomeda, long after most stars have died, these red dwarfs will still be shining. Webb's mapping of star formation zones provides a snapshot of Andromeda's current activity. The galaxy is not dormant. It is actively creating new stars, albeit at a slower pace than in its youth. When the collision with the Milky Way occurs, this process will accelerate dramatically. Gas clouds from both galaxies will collide and compress, triggering the most intense burst of star formation Andromeda has experienced in billions of years. But gas clouds contain more than just hydrogen. They are chemical factories, producing complex molecules. And what Webb found floating in those clouds is astounding. Space is not empty. Between the stars floats a thin soup of atoms, molecules, and dust grains. Most of it is hydrogen, the simplest and most abundant element in the universe. But sprinkled throughout are more exotic compounds: carbon monoxide, water ice, methane, ammonia, organic molecules that, under the right conditions, could lead to life. The James Webb Telescope specializes in detecting these molecules. Its infrared spectrometers can identify specific chemical compounds by their unique absorption and emission signatures. When light from a background star passes through a molecular cloud, the molecules absorb specific wavelengths. The resulting spectrum is like a barcode, revealing exactly what compounds are present. In Andromeda's molecular clouds, Webb found an abundance of carbon-rich moleculous polycyclic aromatic hydrocarbons, as mentioned earlier, but also simpler compounds like methane and ethane. These molecules form in the atmospheres of carbon-rich giant stars. When these stars shed their outer layers, they release these compounds into the interstellar medium. Methane is particularly interesting. On Earth, methane is produced primarily by biological processes: bacteria in swamps, digestive systems of animals, decomposition of organic matter. In space, methane forms through non-biological chemistry, but its presence still indicates complex chemical processes. The molecular clouds in Andromeda are cold, just 10 to 50 degrees above absolute zero. At these temperatures, many molecules freeze onto dust grains, forming icy mantles. These ices contain water, carbon monoxide, methane, and more complex organics. When stars form from these clouds, the ices sublime and become incorporated into protoplanetary disks. Eventually, they end up in comets, asteroids, and planets. This means every solar system forming in Andromeda right now is being seeded with organic molecules, the building blocks of life. Whether life actually arises is a different question, one that depends on countless other factors, but the raw materials are there. Webb also detected emission from carbon monoxide, a molecule that forms easily in space when carbon and oxygen atoms combine. Carbon monoxide is abundant in star-forming regions because it can survive in relatively warm gas. It serves as a tracer, allowing astronomers to map the distribution and motion of molecular clouds. By measuring the Doppler shift of carbon monoxide emission, astronomers can determine how fast the gas is moving. This reveals the internal dynamics of molecular clouds. Some regions are collapsing, falling inward under their own gravity. Others are expanding, blown outward by stellar winds. Still others are rotating, spinning around a central protostar. The chemical composition of these clouds also reveals Andromeda's history. Molecules containing heavy elements like nitrogen, oxygen, and sulfur could only form after multiple generations of stars had lived and died, enriching the galaxy with these elements through supernovae. The abundance of these molecules in Andromeda is higher than in the Milky Way, supporting the theory that Andromeda has undergone more intense star formation and more violent mergers. Ammonia was detected in several clouds. This molecule consists of nitrogen and hydrogen. It forms in cold, dense gas where nitrogen atoms can react with abundant hydrogen. Ammonia is a key ingredient in prebiotic chemistry. Experiments on Earth have shown that ammonia, when combined with other simple molecules and subjected to energy sources like lightning or ultraviolet light, can produce amino acids, the building blocks of proteins. Does this mean Andromeda could harbor life? Possibly. The galaxy has 1 trillion stars. Even if only a tiny fraction have planets, and only a tiny fraction of those planets are habitable, the numbers add up. There could be millions of worlds in Andromeda where conditions are suitable for life as we know it. But we will never know for certain. Andromeda is too far away. Even our most powerful telescopes cannot resolve individual planets around stars in other galaxies. We can study the galaxy as a whole, map its structure, measure its composition, but the question of life remains unanswered. What we can say with certainty is that Andromeda's molecular clouds are chemically rich environments. They contain the ingredients necessary for complex chemistry, possibly even biochemistry, and they are being constantly replenished by dying stars, creating a cycle of matter that has persisted for billions of years. But these clouds are not static. They are being disturbed by powerful forces emanating from the galactic core forces that are blowing gas out of the galaxy entirely. Galaxies breathe. They pull in gas from intergalactic space and expel it back out in powerful winds. This cycle regulates star formation, controlling how fast a galaxy can grow. Without these winds, galaxies would convert all their gas into stars too quickly, burning out and dying young. The winds provide a release valve, slowing the process. Andromeda has galactic wind streams of hot gas flowing outward from the core, heated to millions of degrees and accelerated to hundreds of miles per second. These winds are driven by two main sources: supernovae and black hole activity. When massive stars explode as supernovae, they release enormous amounts of energy. A single supernova can outshine an entire galaxy for weeks, but most of that energy is not in light. It is in kinetic energy, explosive force that blasts the star's outer layers into space at thousands of miles per second. When multiple supernovae explode in the same region over a few million years, they create a superbubble. The expanding shock waves from individual explosions merge, creating a cavity hundreds of light years across, filled with hot, thin gas. This gas is under pressure. It expands outward, breaking through the galactic disk and escaping into the halo. This process is called supernova-driven winds. It happens in all star-forming galaxies. The Milky Way has these winds. Andromeda has them. Even small dwarf galaxies experience them, though in those cases the winds can be strong enough to expel most of the galaxy's remaining gas, shutting down star formation entirely. But there is a second source of galactic winds: active black holes. When a supermassive black hole feeds, it does not consume everything that falls toward it. Some of the material is accelerated and ejected in powerful jets or wide-angle winds. These black hole-driven outflows can be far more powerful than supernova winds. Andromeda's black hole is not highly active right now. It is not producing the kind of powerful jets seen in quasars and active galactic nuclei, but it is producing winds. Even a weakly active black hole can generate outflows. Gas falling toward the black hole heats up through friction and magnetic interactions. This hot gas expands and pushes outward, creating a pressure-driven wind. Observations with X-ray telescopes detected these winds: hot gas flowing out from Andromeda's core at speeds of several hundred miles per second. The wind is not continuous. It comes in bursts, correlating with the X-ray flares discussed earlier. When the black hole experiences a feeding event, it produces a stronger wind. During quiet periods, the wind weakens. The James Webb Telescope added a new perspective by observing the winds in infrared. Webb can see cooler gas that X-ray telescopes miss. This revealed that the winds are more complex than previously thought. They are not smooth flows but structured into filaments and bubbles. Some regions have high densities, others are nearly empty. The winds carry away heavy elements produced by supernovae: carbon, oxygen, nitrogen, iron. These elements are expelled from the galaxy and deposited in the intergalactic medium. Over billions of years, this process enriches the space between galaxies, creating a reservoir of enriched gas that can eventually fall back and trigger new star formation. But the winds also carry away potential star-forming material. Every kilogram of gas blown out of the galaxy is one less kilogram available to form new stars. This creates a feedback mechanism. When star formation is high, many supernovae explode, creating strong winds that expel gas and reduce future star formation. The galaxy self-regulates. In Andromeda, the winds are currently moderate, not strong enough to completely shut down star formation, but significant enough to affect the galaxy's evolution. If the central black hole becomes more active, the winds will strengthen. An actively feeding black hole can produce winds powerful enough to clear the entire central region of gas, creating a dead zone where no stars can form. This might explain why Andromeda's core has relatively little ongoing star formation, despite containing dense gas clouds. The winds from the black hole might be preventing that gas from collapsing. The gas is there, but it is being constantly stirred up by outflows, unable to settle and fragment into new stars. When the Milky Way and Andromeda collide, the winds will intensify dramatically. The collision will funnel vast amounts of gas toward both galactic centers. The black holes will feed at much higher rates. The resulting winds could blow out a significant fraction of both galaxies' gas, potentially shutting down star formation for hundreds of millions of years after the merger. These are not gentle breezes. They are cosmic hurricanes reshaping entire galaxies. And they are not the only mysterious signals coming from Andromeda's core. Neutrinos are ghost particles. They pass through matter as if it were not there. Right now, trillions of neutrinos are streaming through your body every second, coming from the core of our sun, from distant supernovae, from nuclear reactors, from cosmic ray interactions in the atmosphere. Almost all of them pass through Earth without interacting with a single atom. Detecting neutrinos requires enormous specialized detectors. The IceCube Neutrino Observatory in Antarctica consists of over 50 sensors buried deep in the ice, monitoring a cubic kilometer of frozen water. When a neutrino occasionally collides with an atom in the ice, it produces a faint flash of blue light. IceCube detects these flashes and works backward to determine where the neutrino came from. Most neutrinos detected by IceCube come from the atmosphere or from our sun, but occasionally IceCube detects high-energy neutrinos from deep space. These astrophysical neutrinos carry energies millions of times higher than solar neutrinos. They are produced in the most violent environments in the universe: supernova remnants, gamma-ray bursts, active galactic nuclei, and apparently from Andromeda. In 2006, IceCube detected a burst of high-energy neutrinos coming from the direction of Andromeda. The timing was remarkable. The neutrino burst coincided with the first major X-ray flare from Andromeda's central black hole detected by Chandra. Then, in 2013, it happened again: another neutrino burst, another X-ray flare, both from the same source. This correlation is deeply significant. Neutrinos are produced when high-energy particles collide with matter or radiation. In an active galactic nucleus, protons can be accelerated to enormous energies close to the speed of light. When these ultra-relativistic protons collide with photons or other particles, they produce pions. Pions decay into muons and neutrinos. The muons decay into electrons and more neutrinos. The fact that neutrinos arrived at the same time as X-rays suggests a common origin. Some energetic event at Andromeda's core is simultaneously producing X-rays and accelerating particles to energies high enough to create neutrinos. The most likely explanation is particle acceleration in the accretion disk around the black hole or in jets emerging from the poles. But here is the mystery. Andromeda's black hole is not supposed to be active enough to produce detectable neutrinos. The neutrino flux detected by IceCube is consistent with a moderately active galactic nucleus, far more active than what X-ray observations suggest. Either the black hole is more active than it appears, or we are witnessing a rare transient phenomenon. Recent analysis published in 2025 examined the correlation in detail. The researchers confirmed that the two neutrino bursts are statistically significant and genuinely associated with Andromeda. This is not a coincidence. Something at Andromeda's core is accelerating particles to extreme energies and producing both X-rays and neutrinos. Theories abound. Perhaps the black hole is producing intermittent jets. These jets might be too faint or too narrow to be detected by radio telescopes, but powerful enough to accelerate particles and create neutrinos. When the jet turns on, we see an X-ray flare and a neutrino burst. When it turns off, everything goes quiet again. Another theory suggests the neutrinos are produced when clouds of gas fall into the black hole. As the gas spirals inward, magnetic fields accelerate some particles to ultra-high energies. These particles escape before crossing the event horizon, flying outward and eventually colliding with surrounding gas and radiation, producing neutrinos. The neutrino connection transforms our understanding of Andromeda's black hole. We are not looking at a completely dormant object. We are looking at something in transition. A black hole waking up, beginning to feed, starting to produce the kind of high-energy phenomena characteristic of active galactic nuclei. If this trend continues, Andromeda could develop into a full-fledged active galaxy within a few million years. The black hole would blaze with radiation across the electromagnetic spectrum. Jets would extend hundreds of thousands of light-years into space. The galaxy would transform from a quiet spiral into one of the brightest objects in the local group. Neutrinos offer a unique window into this process. Unlike photons, which can be absorbed or scattered, neutrinos travel in straight lines from their source to our detectors. They provide direct information about particle acceleration processes happening at the black hole. Future neutrino observatories will monitor Andromeda more closely. If additional bursts are detected, especially if they correlate with X-ray flares, it will confirm that the black hole is entering a new phase of activity. And it will provide crucial data for understanding how supermassive black holes transition from dormant to active states. The ghosts are speaking. We just need to listen carefully. And what they are telling us changes everything we thought we knew about how galaxies evolve. Andromeda is not unique. It is a template, a laboratory where we can study processes that happen in galaxies throughout the universe. What we learn from Andromeda informs our understanding of billions of other galaxies too distant to study in such detail. The discovery that Andromeda has consumed over 100 smaller galaxies confirms a fundamental principle of galaxy evolution. Galaxies grow by cannibalism. The largest galaxies in the universe today are not pristine objects that formed at their current size. They are monsters assembled through billions of years of mergers and acquisitions. This process, called hierarchical galaxy formation, is a cornerstone of modern cosmology. In the early universe, small galaxies formed first. Over time, they merged into larger galaxies. Those larger galaxies merged into even larger ones. The process continues today, though at a slower rate as the universe expands and galaxies move farther apart. Andromeda provides direct evidence for this model. The stellar streams in its halo are fossil records of past mergers. Each stream represents a galaxy that was destroyed, its stars scattered across Andromeda's outer regions. By counting these streams and estimating when they formed, astronomers can reconstruct Andromeda's growth history. The chemical enrichment seen in Andromeda's stars tells another part of the story. Early galaxies had low metallicity because only hydrogen and helium existed after the Big Bang. Every generation of stars that lived and died added heavier elements to the galactic gas. By measuring the metallicity of stars in Andromeda, astronomers determine when those stars formed and what the chemical composition of the galaxy was at that time. Andromeda's relatively high metallicity compared to the Milky Way suggests it underwent more intense star formation earlier in its history. It burned through its gas faster, creating more massive stars, producing more supernovae, enriching the interstellar medium more rapidly. This supports models suggesting that larger galaxies evolve differently than smaller ones. The activity level of Andromeda's black hole also informs galaxy evolution models. We now know that almost every large galaxy contains a supermassive black hole. We also know that the mass of the black hole correlates with the mass of the galactic bulge. This suggests black holes and galaxies co-evolve, influencing each other's growth. When a black hole is actively feeding, it produces winds and jets that can suppress star formation. This feedback mechanism prevents galaxies from converting all their gas into stars too quickly. Without it, galaxies would burn out and die young. The winds expel gas that would otherwise form stars, regulating the galaxy's growth rate. Andromeda's transition from dormant to moderately active provides a real-time example of this process. The increasing X-ray emission and neutrino bursts show that the black hole is beginning to affect its surroundings more strongly. If the activity increases further, it could shut down star formation in the galactic core, transforming Andromeda from a star-forming spiral into a quiescent elliptical. The upcoming collision with the Milky Way offers an even more important laboratory. Astronomers will witness a major galaxy merger in real time, albeit over billions of years. Simulations predict what will happen, but observations of the actual event will test those predictions. We will learn how gas behaves during collisions, how star formation is triggered or suppressed, how black holes interact and merge, how dark matter halos combine. This knowledge applies to every galaxy merger happening anywhere in the universe. By studying Andromeda and the Milky Way, we learn about galaxy evolution in general. The James Webb Telescope observations add infrared data to the picture. We can now see through dust and observe regions invisible to previous telescopes. This reveals hidden star formation, complex chemistry, and structures that challenge our understanding. Every galaxy tells a story. Andromeda's story is one of violence and growth, of cannibalism and renewal, of a sleeping monster beginning to wake. It is a story that has played out countless times across the universe, and it is a story that our own galaxy will soon experience firsthand. The collision between the Milky Way and Andromeda is not an isolated event. It is part of the grand cycle of galaxy evolution that has been ongoing for over 13 billion years, and it will continue for hundreds of billions of years to come. We are witnessing a single chapter in a story far larger than our Selviza story, written in starlight and dark matter, in X-rays and neutrinos, in dust and gas and ancient stellar streams. The universe is a violent place, but from that violence comes creation, and one final truth remains to be stated. Look up on a clear autumn night. If you are far from city lights, you might see it. A faint smudge of light in the constellation Cassiopeia, easy to miss if you do not know where to look. That smudge is Andromeda, 2.5 million light-years away, yet close enough to see with your naked eye. You are looking at light that left that galaxy when our ancestors were barely human, before we built cities or wrote languages, before we discovered fire or crafted tools. That light has been traveling through space for 2.5 million years, crossing an incomprehensible distance, just to reach your eye tonight. And while you watch, Andromeda is watching back. Its trillion stars shine in the darkness, many of them hosting planets of their own. If life exists on those worlds, if civilizations have arisen and fallen, they too might be looking across the void toward our galaxy, seeing us as we were millions of years ago. The James Webb Telescope has given us the clearest view of Andromeda ever achieved. We have peered into its core, seen the monster lurking there, watched gas spiral into the black hole, mapped stellar nurseries hidden by dust, and detected signals that terrify and fascinate in equal measure. What terrifies scientists is not that Andromeda is coming toward us. We have known that for over a century. What terrifies them is what Webb revealed about the galaxy's current state. A black hole waking up, X-ray flares increasing, neutrinos streaming from the core, star formation accelerating in specific regions, galactic winds strengthening, signs of instability that models did not predict. Andromeda is changing. Right now, in real time by cosmic standards, the galaxy we observe today is not the same galaxy it was 20 years ago. The black hole is more active, the core is more turbulent. Something is happening. When the collision occurs, whether in 4 billion years or 10 billion years or something in between, it will not be two stable spirals gently merging. It will be two dynamic, evolving systems already undergoing internal transformations. The violence will be amplified by the active black holes, the disturbed gas dynamics, the ongoing mergers with satellite galaxies. Humanity will not witness this event. Our species may not survive the next few thousand years, let alone billions. Even if we do, even if we spread across the stars and become a spacefaring civilization, we will face the death of Earth long before the galaxies collide. Our sun will destroy its own planets within 1 billion years. But the knowledge we have gained about Andromeda is not for us. It is for whoever comes after the civilizations that might arise on other worlds, the descendants of humanity, whether biological or artificial, who will populate the galaxy in the distant future. They will inherit this knowledge. They will watch the collision unfold. They will witness the birth of Milkomeda, and they will remember that we were here first, that we looked up at the night sky and asked questions, that we built telescopes to peer into the hearts of distant galaxies, that we discovered the truth about our cosmic neighbor. Andromeda is on its way. The great black holes are stirring. The collision has already begun, not in fire, but in the vast, invisible halos where galaxies first touch. These are not prophecies or metaphors. They are measured realities, confirmed by observation, supported by data, and verified again and again by independent eyes. The universe is far larger than intuition allows, more violent, more beautiful, and more unforgiving. And within it, we exist as brief sparks, tiny lives on a modest planet, circling an unremarkable star inside a galaxy already committed to its fate. 4 billion years from now, the night sky will no longer be familiar. Andromeda will sprawl across the heavens. New suns will ignite as old systems are torn apart. At the center, the supermassive black holes will spiral, circle, and finally unite in a single gravitational roar. From the wreckage of two galaxies, something new will be born, a vast, reshaped cosmic home. This is not speculation. It is destiny written in gravity, as unavoidable as time itself. Through the eyes of the James Webb Space Telescope, we are not just seeing deeper into space, we are glimpsing the future, and it is at once terrifying and sublime.